Good morning, everyone. It's my pleasure to introduce Alma Hodzic, who is a scientist too here in the Atmospheric Chemistry and Environment Laboratory. Alma received her PhD in October 2005 from the École Polytechnique in Paris. And in her work there, she was doing aerosol modeling over the Paris region. And then soon after her PhD, she came to NCAR. So she's been at NCAR since December 2005, where she first did an ASP postdoctoral fellowship. She focused on doing aerosol modeling over Mexico as part of the Mirage field campaign. And then in October 2007, she was hired as a scientist one in ACD. And as part of her work since that time, she's been using models to better understand aerosols and air quality. And she, as part of that, has helped develop the aerosol and improve the aerosol schemes in the WRF Chem model, and has contributed to the analysis and forecasting for the Beacon and NOMADS field campaigns. So today, she's going to take on this very complex subject of looking at organic aerosols, their formation processes and their destruction processes. And so without further ado, I'd like to hand it over to Alma.
Thanks, Mary, for this nice introduction. So today I'm going to discuss about organic aerosols, their importance, and how well we understand their formation and removal in the atmosphere. And we all have experienced some sort of aerosol pollution in our cities. And here I put some examples of a few cities where you can see this gray-brown cloud of haze and smog. And this cloud is actually composed of tiny little particles that we call aerosols that have a size is basically ranging between 50 and 500 nanometers. And these aerosols are either primary aerosols, and we call them primary because they're directly emitted from sources, from natural sources or anthropogenic sources. And they include, for example, soot or black carbon, dust, sea salt, and some organic species. We also have secondary aerosols, which are chemically formed aerosols through either simple chemistry for sulfate, nitrate, and ammonium, or much more complicated chemistry, as we will see later on, for most organic species. Here is a picture of an aerosol through a microscope. And you can see, as I told you, aerosols are mixtures of many different compounds. And you see here that we have soot here in dark, which is coated with a layer of sulfate in red, and then organic species in blue here. So these aerosols in the atmosphere, they pretty efficiently scatter and absorb solar radiation. They can modify atmospheric stability and temperature profiles. They can also serve as cloud condensation nucleus, CCN, and modify the lifetime and formation of clouds, precipitations as well. And so for all of us that work on meteorology and climate questions, these aerosols are very important. They also, small particles, especially submicron particles, can penetrate our lungs, and therefore they're also very bad for our health. And here is an example of a study that estimates the premature deaths due to different environmental risks. And here is the deaths due to particles. And you see in 2010, about 1.5 million people died due to air pollution due to aerosols. This is projected to even double in the future, in the 40 years. And aerosols are going to become one of the major health issues, even more important than drinking unsafe water, for example. If you look at the total mortality in the world, there are 55 million people that die each year. And if you think that aerosols kill basically 1.5 to up to 4 million of people, this is a really serious concern for health. Ozone, in comparison, is a much smaller concern for health. So that's why we really need to understand these aerosols. So now let's see what is composing this aerosol pollution. If you look at the measurements from the aerosol mass spectrometer, all over the world, we see on these pie charts that aerosols are basically composed of sulfate, organics, nitrate, and ammonium. And here in green, you see that organics in many places, even like in Mexico City, it's basically the major fraction of the aerosol. And we understand more or less sulfate, but organics are much more complicated, as we will see later on. So what matters really for health and climate impacts is to be able to estimate how much has SOA increased, or organic aerosol, increased due to human activity or since the pre-industrial. And there are many different ways to estimate this. The simplest way is basically to consider correlations between organic aerosols and ozone. And those are measured in many field campaigns. We find slopes ranging from 30 to 150 micrograms per cubic meter per ppm of ozone. These two species are correlated because they both result from complex chemistry. Those are secondary species in the atmosphere. And we know also that ozone has increased by 25 ppb since the pre-industrial. And very easily from these, we can estimate that SOA due to human activity has increased by 1 to 4 micrograms in the troposphere. And that leads us, if we integrate it over the northern hemisphere, to up to 1 teragram of anthropogenic or anthropogenically controlled SOA due to human activity. Gladly, there are more complex ways to estimate this, and those are models. So a recent study using a 3D model, global model by Spraklin et al., and also constraining this model by measurements, AMS measurements and carbon-14 measurements at the surface, estimated this human activity is actually leading to 1.3 teragrams, which is pretty similar to this other estimate. The only problem here is these estimates are actually not based on process-level understanding of SOA formation. So these are top-down constrained by observations. And so let me show now what our current models do. So here is a very recent study by Smith and Bond, 2014, where they actually discussed about the end of the age of aerosols. And they used the IPCC RCP 4.5 scenarios, and they show that basically we have the forcing, direct forcing by organic carbon, which is pretty small, minus 0.1 here, and it's way smaller than that of sulfate. When you look at these results, first thing that strikes you really is that this is much smaller compared to the relative abundance of these organics compared to sulfate in the atmosphere. So it's pretty inconsistent. Sure enough, in their study, they neglected the formation of secondary organic aerosols because that's too complicated. They said it was negligible, and their only source was the biomass burning aerosol. We now know that biomass burning is about 30 teragrams, and SOA, it's a much larger source. So let's see other modeling studies. So basically, just to show you the motivation of my work here, a recent study again, Tsigaridis, 2014, compared many state-of-the-science global models, and we participated in this exercise with the NCAR model. And you can see here the predicted organic carbon profiles integrated globally. So you see that these models give very different answers. They vary by a factor of 10 near the surface. So this is very important. Surface concentrations are important for human exposure. And they also vary by a factor of 100. And in this up here, this is relevant to climate forcing. If you take one of the models, which is the GECKO-A, which is the one that makes most of the aerosol here, it's the brown here, another separate study estimated actually how this model compares to observations. Here I'm showing you ratios between observation and the model. And you can see that for all of these field campaigns, different locations, polluted, biomass burning, remote, you see that the model is basically under-predicting heavily by a factor of 2 to 10 the observed SOA. So there is really a need to develop better understanding based on process levels to simulate current SOA. This is important, of course, to robustly estimate how much SOA has increased from the pre-industrial, but also it's important to understand how SOA will evolve under future emission scenarios and also with the future temperature changes. So this is really where my research comes in. And in the past 2 or 3 years, I've been really focusing on trying to develop new process level insight into SOA formation, growth, and removal based on our best understanding of the chemistry. And I'm using for that explicit chemical modeling that we do in ACD. It's a model GECKO, and I will come back to this. And basically, my work focuses in 3 areas. To understand SOA budgets, we need to understand how they are formed. So first part of my talk is going to focus really on the formation of SOA from different precursors, on this complex chemistry, how we represent it, and how we can do a better job. And then the second and third part of my talk will look at the aging of these organic species in the atmosphere and how their property changes, how they become more soluble and more vulnerable to removals. And I will also discuss in the third part of my talk how these species are sensitive to the multi-day sunlight exposure, because they're out there for few days or up to a few weeks. And then we'll use this process level understanding to develop parameterizations for 3D models, and at the end I will show you a global SOA budget estimate in a global model. So let's see now, what must be known to model SOA formation? And I'm going to illustrate this by giving you an example for terpene compound. Terpenes are emitted, basically those are VOCs emitted by trees. They're very common, they make a lot of SOA. And I'm going to show you this formation in this 2D space that I like a lot. On the x-axis, we have the volatility, which is basically a measure of a vapor pressure. this parameter tells you how organic vapors and aerosol partition between each other. So on this side, high volatility means we are in the gas phase. So we have this space here. When we are in the particle phase, we have lower volatilities. And there is a transition area in between where they go back and forth between particle and gas phase. On the other axis, I have the solubility. And as I told you, solubility is another parameter that tells us how vulnerable these species will be to removals. So let's see now. So we have our terpene, C10 here. It's a highly volatile species. So it's here on this plot, not very soluble. It's a gas species, and it's going to be in the atmosphere. We have other emissions. For example, we have different biogenic VOC. We have also some aromatics and alkanes, which are anthropogenic species, and some dirtier fuel also that are sometimes not really like these N-alkanes. I'll talk about this later, that are not always in our emission inventories. So let's see what happens now. Here I'm showing you the results from GECKO just 15 minutes after we oxidize this species. So you see the cloud of points. These are all of the products, different species that came out from just this one precursor. And you see that they are actually, they moved a little bit in this space. They are less volatile, and they're also more soluble. You also see that they have few functional groups. Functional groups, that means that they attach oxygen, nitrogen, and other compounds to this carbon skeleton. And let me show you what happened to them. So each of these species that we now call semi-volatile organic compounds, because now their volatility has decreased, they all go different type of reactions in the atmosphere. They can get oxidized, so oxidation by OH and ozone typically, or NO3. They can also fragment. So the oxidation has the tendency to give them, attach more functional groups, more oxygen, so they become heavier, more sticky. That's why the volatility drops. That's why also they become more soluble. On the other hand, fragmentation is going to break these molecules in two, or they're going to lose some carbon, and they're going to become smaller, less sticky, and more volatile, and they're going to end up making CO and CO2. So they will never make it to the aerosol. And then what happens with the ones that are sticky, SVOCs? So those guys can partition, they can condense onto pre-existing organic aerosols. And when they're sufficiently low volatile, they go through this transition zone here. They can actually partition back and forth. They are in thermodynamic equilibrium with the aerosol. So, and then once this aerosol is very little volatile, it stays in the atmosphere, and then it will undergo some removal processes. So all of these processes have to be represented in 3D models. And in addition to this, so here let me show how this story ends. So here we are at 15 minutes. 1 hour later, you see that we have more and more species here. 2 hours later, we have even more. 5, we have more. 10. Now the precursor is almost all gone. Here, the red dot, the green dot. And 20 hours, 30 hours, we have basically moved a lot of this material. We oxidized it, attached a lot of functional groups, a lot of oxygen, moved it toward this particle space. So we made we made the aerosol here. And so how do we represent this complexity in 3D models? So we have, of course, several options. We can go fully explicit, where we have resolve all of these reactions, and that's what GECKO does, or a master mechanism. But those are very expensive to run these days in 3D models. We can also go on the other side of the spectrum. We can do very simple. We can have just an SOA mass tracer. And for that, we can just constrain it with the measurements. We know the ambient measurements of SOA to CO, or as I showed you, SOA to ozone, those correlates. So we have some parameterization that we can use to just simply track SOA mass. But what we really want to have in 3D models is some predictability. We want to know how these aerosols will be sensitive to NOx, to temperature. So we use intermediate complexity parameterizations. And I will just show you in a minute what those are. One common thing to them is they're all fitted to smog chamber data. And what's a smog chamber experiment? You actually basically put some of the precursors, like here terpene, and you see after 10 hours how much SOA you got. So that's your yield. The problem of the chambers is that they also have walls, and I showed you here that these pieces were very sticky. They're going to stick to the aerosols, but they're going to also stick to the walls. And so we're going to have huge losses in the chamber data, and these yields are not going to be correct. The problem is that we don't know how to correct them now. It's a big issue in the community. But still, we are using these yields from the chambers. So how do we represent all this chemistry? It's done right now in a very simple way in regional and climate models. We typically have in a traditional model one reaction, one-step oxidation reaction. So we have our VOC precursor, which can get oxidized by OH or ozone or NO3 also, and it gives us some gas species products. the amount, how much we get of these species, as I told you, is fitted to smog chamber data. So it's constrained by something. And then these species, they fall into different volatility bins. That's why we call this also volatility basis set. They can then partition to make SOA. The one that's the least volatile, this guy here, is going to make some SOA. But we actually know now that this is not sufficient. We are under-predicting by a lot the observed SOA mass. So what some people do, and this is now totally ad hoc and artificial, they say, yeah, there is a lot of this aging and chemistry is going on for days in the atmosphere. And so let's just move this mass from the highly volatile species into less volatile one by just reacting them another time with OH with some rate constant that they basically tune. The problem of this artificial aging is that it's totally made up. It's not constrained at all. So it's totally unclear which precursor should be aged and at what rate, what species are we getting, what are the properties of these species. We are certainly getting way more mass. So let me show now, during Mexico City, how this traditional approach compares to the data. So here, we did a study where we compared a regional model, and in black you have observed SOA integrated within the whole boundary layer, so you have the mass. And I'm showing you here the results of the regional model, including anthropogenic and biogenic precursors, and you see that the model is by a factor of 5 or more under-predicting the amount of SOA that's in the city. That's to be expected, now we know. There are ways to fix this. As I told you, you can age it artificially. So here, we age it here in blue, and you are getting, of course, more mass. I could have aged this a little bit more aggressively. I would have gotten the exact measured mass. And so this is from what's actually, we are using here just the precursors that are available in the emission inventories. There is another way to do this. We can add additional precursors. So we know for Mexico City, it does make sense. There are some species, which are these N-alkanes, these longer carbon chains that come from dirtier fuels. In Mexico City, there are a lot of dirty cars. And we can add those and age them as well. And so here is what we get. So here, again, I'm showing you now this time SOA concentration in black here. You see the maximum during the afternoon. And then I'm showing you the traditional, of course, is under-predicting. And then we have these two lines, red and green, that are showing what results we are getting with this additional precursor with aging. I applied 2 different aging coefficients that are actually advised and published in the literature. And you see that you are getting a big range of possible values. So my point here is really that this is very unconstrained. So our state of science current models are based on basically ad hoc approaches that are tuned to match today's observations. Sure, that might give you the right answer, but probably for the wrong reasons. And the problem is that we cannot use these approaches to predict effects of future emission changes or future temperature changes and how this is going to all play out for the climate. So this is what I was trying now to fix in my, my research. And my approach was trying to find additional constraints from explicit modeling. And I'm using this Gecko model. Gecko is the generator, basically, of explicit chemistry that was developed here at NCAR 20, 30 years ago. And now it's being also developed at the University of Paris by Bernard Ramon and his students. And basically, the idea, it's a mechanism, it's a model that writes, self-generates the chemistry of many VOC precursors, so aromatics, alkene, alkanes, and also of their products. It's doing that based on our understanding of the chemistry, based on laboratory data, structural activity relationships, and we end up having huge mechanisms. For example, for alpha-pinene, which is another biogenic precursor, the mechanism size contains 500,000 species and more than 3 million reactions. So we run this in a box model, of course. And in a box model, as you all are probably used to it, we run different types of simulations. Eulerian simulation over a city where we look at the production and the emission processing over the city. And then we also do Lagrangian simulations where we detach an air parcel and we don't emit anything into this air parcel. We just look at it aging and what the chemistry does to it. And we use Gecko to address many questions like quantify contribution of various precursors. We also ask the questions about separate individual processes, and once we decide that something is really important and relevant, we try to parameterize it, and we put it in 3D models, into WRF-Chem, regional models, or global models, and we look at the effects, and also, this is the way also to evaluate it with ambient measurements. So that's basically the approach. So now, before I show you Gecko results, I also want to convince you that Gecko actually does a pretty good job. It's been validated with smog chamber experiments that were dedicated really to do that. And here is an example, for example, of a comparison of yield of SOA made in Gecko in purple here and measured in black here once they have factored in the wall losses. As I told you, that was an important factor. And you see that for different precursors and different carbon chains, this works pretty well. So now let's see how we apply, what insights we are getting from this model. And let's go back to my Mexico City example that was showing that you had several options how to get the observed data. So what does Gecko say? Here, again, I'm showing you SOA concentrations. This is an average over the whole months of March in black. And I'm showing you that here in blue, Gecko is predicting that from traditional precursors that were originally in the emission inventory, we could not make much SOA. When we include these dirtier fuels and alkanes, longer chain and alkanes, we do actually make much more mass. Looks simple. So let's just take a slice here at 3 o'clock in the afternoon and look where this mass is as a function of the carbon number. In darker colors here in shading, you have aerosols. So you see that in the smaller carbon numbers here, we have only 10% of the mass. So this is this traditional blue. And we have 90% of the mass that's coming from longer chain and alkanes. So this is consistent. But then what happens in the outflow? You see that in the outflow, actually, the traditional have now produced much more SOA. And we have a 50-50 contribution, basically, from these two different fuels. So my point here is that you really have to understand how different precursors are making SOA. You cannot just age all of them in the same way and just stick it there in the model and be happy. The behavior changes if you are closer to the sources and if you are downwind. Closer to the sources, that's important for air quality. Downwind is important for climate. So we can get some really good insights from this type of modeling. Another example I wanted to show you is also the question between what is the production of SOA downwind of a megacity, Mexico City here in red, and what is the production downwind of a forest? So this was the Beacon case in Colorado. And here I'm showing you the mass of SOA produced downwind of this city, basically regionally. And you see, this is a Lagrangian simulation. So we detached our plume in the afternoon, and now we are just doing chemistry. And you see that the mass of SOA has increased by a factor of 5 downwind of Mexico City. So Mexico City produced a lot of SOA regionally. What happened downwind of a forest? We see that the behavior is very different. We have only an increase by 1.5, and it's much less important. So the point here is really that Gecko tells us that these sources behave very, very differently. And so the idea was then to try to parameterize this understanding, all these case studies that we did into a global model, into a regional model. And for that, I did many idealized case runs with Gecko, where we run for given precursors like alpha-pinene, or mixtures like terpenes, where we have several precursors. And we look at the yields coming from this and behavior coming from these precursors. And just I wanted to show an example here, like, for example, for terpenes and toluene, that SOA yields, they're going to also be very dependent on the NOx, because when we have more or less NOx, we are making different chemical compounds. And you see that when we have low NOx, we are having higher yields, we are making more SOA, and as we are at higher NOx, we are making less SOA. So all this information has to come somehow in our 3D models. And so just wanting to show you really a simplest, we are working on this, we are developing different approaches with different complexity. I just wanted to show you the simplest one. And this is basically a single generation mechanism that we can develop from Gecko. And you remember my plot for terpenes here. So what we can do, we can just bin the material that's produced here within volatility, based on their volatility, in a volatility basis set. Like it was done for traditional models. They had 4 products. Now we decide to have more, 6, to kind of cover larger, wider space here. And we can do that. We can just have one step reaction, oxidation, where we actually produce these pieces, and we base this on Gecko. So let's see how it compares. So this is SOA produced after a few days. And you can see here in black is the full Gecko, and then in red is the fit that we just made here. And so it does reproduce pretty well the full Gecko. It also reproduces its properties in terms of volatility and so on. I don't want to go too much into details here. How it compares to traditional, so this is a traditional from chambers. This is traditional with aging. All of this mass here that they age actually came up from just imagination, so it's from the tuning. So this is very dangerous because you can get a big range. Now we know from Gecko at least what we think could be true. And so Just a quick example here, and this is still a work in progress actually. I wanted to show you how the results, when we put this in a 3D model, differ between traditional with the artificial aging of precursors. So here is a simulation with WorfChem for surface SOA in summer 2010. And you see that we have anthropogenic SOA over the southeast. We see some California here. Then we have biogenic SOA here. And when we compare with the observations, so these are improved sites, you see that we are getting a little slight over prediction. But this model, of course, works well with the observation because it was tuned to do so. And then when we look at the parameterization based on GECKO, we see also that we are making a little bit more anthropogenic SOA, less biogenic SOA. We especially see that there is this very different spatial distribution of this aerosol. That's to be expected because they have very different properties. And also when we compare with the data here, it looks a tiny bit better, but it looks pretty good compared to measurement. So my point here is that we really can predict the observations based on first principles and based on real chemistry here, and we can introduce this in a very simple way in 3D models. I don't want you to stop at this good agreement with observations because that's never a measure of success. Of course, there are many missing processes. Aqueous chemistry is not included in these models. There are additional precursors, as we saw, and alkanes, and there are also processes that we are not even aware of. So, but that doesn't really matter. So even if you make more mass, let me show you that that's not a big problem, actually. So let me show you the other side of the story of this budget. Now let's look at the removals. In the community in the past 10 years, most of the people really have looked at SOA formation. 99% of the study have been trying to make more SOA because we really needed more SOA. And very few studies have looked at the removal processes. So we did this in the past 2 years. So we looked at how SOA aged and how that changed that solubility. We also looked how the photolytic removal played a role in this. And let me show you these results. So as you know, currently in 3D models, the main removal process for organic aerosol and for most aerosol is the washout. So the lifetime of SOA with regard to the washout, wet scavenging, rain, basically, it's 5 to 15 days. And then we then try to look at what happens during the aging. We know that these gases, semi-volatile organic compounds, they become very, very soluble. They can also be dry and wet deposited, but we don't really know by how much. So this is really the thing we are going to look at. So if they undergo deposition, they won't be available to make SOA. So indirectly, we'll be reducing SOA mass. This is going to be a sink for SOA. The problem right now is that we do not know what the solubility of these species is. They are very hard to measure, and there are hundreds of thousands of them, so it's very, very difficult. And for that, we used GECKO. We did many studies, actually, and I'm just going to show you how we parameterize this information for use in 3D models. So here I'm showing the volatility-dependent Henry's law or solubility coefficients derived from GECKO for various precursors. So here in green, I hope you see it, we see the precursors isoprene and terpene, so these are biogenics. And then you see alkanes, alkenes, and olefins and aromatics. And you can see, when you look at this, that first of all, biogenics seems to be more water-soluble than the other species. You can also see here that currently in 3D models, people use either 0 or something up to 10 to the 5, 10 to the 5 being for very highly soluble species like hydrogen peroxides, for example. So they use any value in between. They're kind of tuning that. And we see that the values that we are getting actually are even above that. And let me show another plot for the Mexico City case and what the problem with that value is. So here you have the solubility or Henry's law coefficient on the x-axis now, and this is the deposition velocity here. And you see that for our cloud of points that I was showing you before, you see that if you're below 10 to the 5, 10 to the 6, you have relatively low deposition velocities. But if you go a little bit above, where actually a lot of gas species are, these functionalized species, you're starting to have much higher deposition velocities. And these are, now people are starting to measure some of these fluxes. It's very difficult to measure. They're finding for products of isoprene, for example, very recently in Southeast US, they're finding deposition velocities above 1 meter per second, so more like what we are finding. So let's see what this does in the 3D model. Just to give you a sense of the impact of this. So on the top panels here, I'm showing the surface SOA. And here, by purpose, I removed the SVOC removal. It's 0. So you have, again, some anthropogenic and biogenic SOA being formed, southeast mostly. And then when you apply this loss by dry deposition of gases, you see a decrease of SOA concentration on the surface by 20, 40%, and even more for biogenic species. It's much more than the removal by wet deposition of these SVOCs, which is less than 20%. And the net result on SOA surface concentrations, now when you include this removal, is basically a significant decrease in these concentrations at the surface. I just also want to show you, told you, comparison with the observations is not a measure of success, but I just want to show you that we are not totally off. So this is a comparison of the total organic carbon during the summer for these runs. And in black, you see the observations of total organic carbon. And in this pinkish line here, you see a case of the model run with no SVOC deposition. And then the two other simulations that include it actually do a better job. In this particular study, we didn't use Gecko production yields because we didn't have them at the time 2 years ago. And we used basically the traditional with aging approach, 2 different flavors of it, because that was making enough mass. Another point I wanted to make here is that we want to know what is, how this organic carbon deposited at the surface. And if you look at the domain averaged accumulated deposition at the surface over this summer, you can see that most of the deposition occurred actually through dry and wet deposition of SVOCs, more than 60% for anthropogenic, more than 75% for biogenics. So we can say that dry and wet deposition of organic vapors, these SVOCs, it's very important because it mediates the removal of SOA. It's very important to have this well constrained in our 3D models. So let me show you another removal process that we didn't really know what the effect was before. And it seems these days to actually a lot of people are starting to pay attention to this. It's the photolysis. So how does the photolysis interact with the organic aerosols? So in the gas phase, photolysis can basically break molecules. For example, here is an example of pinonaldehyde that's coming from terpenes. And you can see that here a piece of this molecule is going to fall off. The result of this new molecule is going to be more volatile, and it's not going to go into the aerosol phase. It can also have an effect directly on SOA. And we know now from measurements that SOA absorb UV photons. When the photon gets into SOA, into the particle, it can also break bonds. And it can actually kick out some carbon. So we are going to see these particles kind of shrinking. And this is going to be the net loss of SOA mass. So it's a removal process. The only problem is that we don't know how much. So let me show you some experimental evidence from recent chamber experiments. For example, Henry and Donahue in 2012 did this experiment where they made alpha-pinene ozonolysis SOA in the dark. So they made this aerosol 60 micrograms here in an hour. And then they turned on the lights, UV lamps, which started the photolysis reactions. And they saw this decrease. Half of this mass was basically gone. And they hypothesized in their explanations, they said this must be actually due to gas phase photolysis of these organic species. Well, we don't really know if this is gas phase photolysis or aerosol photolysis or something else going on. But this process, my point here is that it's not in anyone's model. So we really want to see if this really matters, if we should be worrying about this, because there is some really heavy evidence from the experiments that it does matter. So with Gecko, we could look separately how much of SOA is gone through gas phase photolysis, how much is gone because of particle phase photolysis, and we can upscale this and run it in a 3D model again. So let me show you an example here for SOA formation from dodecane. So you have SOA here, and we are looking at the formation over 2 weeks of equivalent mid-latitude summertime exposure. So if you look at the red line, this is the amount of SOA that we would get when we have gas phase photolysis on, like in the real world. And then in Gecko, we can just insulate this specific process. We can turn it off. And then we can see this difference. It's basically 20 to 30%. So we see that due to this photolysis that fragment molecules in the gas phase, we are seeing less formation of SOA when we have them on. We also look at the particle phase photolysis. And here we did that by 2 different ways. First way was this orange curve here, in which we photolized all chromophores, whether they were in the gas phase or if they were in the particle phase. We photolized them all with the gas phase photolysis rates, because we don't know really what the photolysis rates are inside the particle. That's still a very active area of research. And so we see an additional removal of decrease in SOA of 50%. The other way we did this was by using measured mass absorption coefficients that we have for this aerosol in ambient conditions. And we assumed that we took a really the smallest value in the range of observed values, and we assumed that every time one photon was absorbed, it led in 1% of cases to breaking of one carbon, kicking out one carbon molecule, which is really like a lower limit. And we scaled this, so we now have this new reaction, which is a photolysis of SOA particle in this case. We scaled this to photolysis of NO2, which we all have in our models. And this is the black line. And we see that even after 1 week, actually this black line is starting to remove a lot of SOA. So this process could be competitive. So we did this for many different precursors. So I showed you here dodecaine C12, but we did it also for alpha-pinene, toluene, and some longer alkanes. And then we estimated the equivalent atmospheric lifetime for our bolder, typical summertime conditions. And if you look at the lifetimes with regard to gas phase photolysis, you see that those are above 10 days. It's in some cases even 2 months. So those are not going really to matter in terms of gas phase photolysis, are not going to be very important in terms of removal of SOA, especially if you're interested in air quality studies, really if you're near source region. Could matter still for longer climate runs. But if you look at the particle phase photolysis, the lifetime is about a week for most of the species. And this is very comparable to the lifetime of, for example, wet deposition. So these guys could be removing a lot of SOA. And so now let me show you an example. When we put this removal of particle phase photolysis, when we put them in the global model. So these are the runs with GEOS-Chem for 2009. Here I'm showing you SOA concentrations over the full year below 5 kilometers. You see US over here. And this is the net loss due to this photolytic loss in percentage. So you see a decrease by 30% over the US and over most of the continents. And it seems that this particle phase photolysis could be potentially an important removal that could remove 20 to 50% of SOA mass. So even if at the beginning we have a much more active production, there are reasonable ways to remove more aerosol in the atmosphere. So unfortunately, we don't have, we still, I mean, this is just a fresh work. So we still have to validate this against measurements, and especially in the upper troposphere, we don't have many measurements of organic aerosols. And here I just want to show you an example of the vertical profiles here. So this is comparing this run for 2009 with a field campaign in Intex B. So Intex B happened 2005, 2006. So these are not really one-to-one comparisons. So you see here the observations are in black. And the model, the reference model without photolysis loss is in blue. And then when you include the photolytic loss, you get this red one. You see how this profile is actually basically shifting in its form, because now we have a way to remove more material from the upper troposphere. So you can imagine now if you have a stronger production everywhere, you want to have a stronger production near surface, but then you want to have some mechanisms where there is not really much rain in this upper troposphere to remove these aerosols. And so this is exactly what these photolysis do. And so now, because I did these 3 separate studies with different tools and different models, I kind of wanted to, the idea now is to put all of this into a single model. So we did an integrative study where we just stick all this into a global model and run for a full year. So this model has revised production yields, has removals, dry and wet removal of SFOX, and also has the photolytic removal. And here I'm just going to show you the budgets. So we have some production of semi-volatile organic gases. They undergo dry and wet removal. They also partition, and the net partitioning to the aerosol. So this is the amount of aerosol that's made, 150 teragrams per year. And we get an aerosol burden of 1.1 teragrams here. Aerosols are also removed by dry, wet deposition, and also photolysis. And what I wanted you to see here is that right now, we actually have SFOC removal by dry and wet deposition it's in terms of magnitude is comparable to the removal of wet removal of SOA, which used to be the only removal before, or the major removal before in global models. So these two are comparable. This term here is also comparable. So we really need to rethink. I mean, this is going to change how SOA is going to be distributed globally and also horizontally and also vertically. So it's important to include all of these processes. So I would like also to come back to comparing my results with some of the previous studies, and because those previous studies didn't have photolytic removal, so let's just look at the burdens without that. And so SOA that we are making from the traditional precursors in these simulations from the new yields is about 2.5 teragrams. And if you remember the Spraklin, he was using top-down estimates constrained by measurements at the surface. He was making 1.8, so these are not so bad. And then traditional with aging of anthropogenic precursors that other studies actually looked at, it was 1.1. So we can make enough SOA, my point being here. And it can, again, be all consistent. So this brings me to my conclusion. And I would like you to remember 3 things from this talk. Is that we really have, from all of this explicit chemistry modeling, we have a new conceptual understanding of the processes. We have seen that we have a stronger growth for example, anthropogenic precursors than from biogenic precursors. We also saw that we are producing all of these intermediate species, semi-volatile organic compounds that are highly soluble and that they can dry and wet deposit. And we also saw that gas, and in particular particle phase photolysis, can modulate SOA production and lifetime. So I showed you also that you really need to stay away from these traditional parameterizations because they are using many tuning parameters, which is okay for maybe today, but it's very dangerous to apply this for any policy making decisions. And one of also important parameters is that GECKO is making, or we are making now, very different aerosols. They're less volatile, and so they're going to have very different sensibility to, for example, changes in temperature. I also showed you that we can fit very easily parameterizations. We can fit yields to explicit chemistry. And now we really need to put this into WRF-Chem and the CSM and do really more comparison with the ambient data. So, so what are the next steps? Let's look first at the next steps related to climate. So basically now we have a framework to use state of science process models that ACD developed to drive our larger scale climate models and to drive our applications in terms of human health implications of aerosol and climate. We are going to continue as a community to work on improving these tools, including aqueous phase chemistry, heterogeneous chemistry, looking at the optical properties that are also very badly predicted by these models. And the fact that our new parameterizations are telling us that SOA is a much more dynamic system. We have a faster production, stronger production, and also stronger removals that we didn't even suspect before. So we are finding this actually in this work. And this is going to change the spatial distribution of aerosols. And we want to know, when we put this into a CSM model, we want to reevaluate the effect of these anthropogenic organic aerosols on climate, for example, regional climate. We want to see where we now fall on these curves, profiles here that I showed you before. We want to see what is the new radiative forcing that we are getting from these aerosols. So that's going to be in the future work, and we have actually proposals that are under revision right now to do that. And now I'm also working, I'm mainly the regional modeler, so I do a lot of studies related to air quality. And all of these developments, I'm actually contributing them to the community through the developments of WRF-Chem, and our version of the code is being really increasingly used for air quality studies. We have several collaborative projects, and these days we are trying to look at SOA formation in more humid regions, for example, in Brazil, during the Go Amazon field projects, or Southeast US, to understand what else is missing there. Are we getting a better understanding of SOA? And we are also going to apply this in highly polluted conditions like China and Southeast Asia, and we have collaborations on this too. And the idea here is just to see if we can predict concentrations in Beijing, which are like 300 micrograms, 10 times those of the one that we have in the US. So how robust are these parameterizations when we put them in these extreme conditions, actually? Another part of my work, also in collaboration with CSU people here, is to understand how different fuel types, how when we choose diesel versus gasoline, or when we have different type of engines, how they make SOA, and which one is more polluting in terms of SOA, and which one is more basically toxic, and how that could change if we were to actually change our future emissions. And as I told you previously before I finish this talk, I would like also to emphasize that we would like really to work with people that are doing measurements, ambient measurements, to get better and more measurements to evaluate some of these hypotheses, especially for the photolysis. And I'm really interested in participating in future field campaigns like ATOM that will be flying high enough, and I will be able to evaluate my upper troposphere concentrations of SOA. And this brings me to my acknowledgements. I would like to thank all my collaborators at NCAR and the universities, and all my colleagues in ACD for great scientific stimulation for all these years, and you too, all of you, because you kind of sat here for an hour with me, so thanks.
Thank you. So are there any questions for Alma? I guess I have one maybe to start with. You're talking about the photolytic processes, and those are very diurnally dependent, yet your box model simulations did not really show any diurnal dependence in the SOA concentrations. Do you have an explanation for that? Or?
Yes, so the explanation is actually, yes, we are aware of that. So we are actually running in idealized conditions when we have a given photolysis rate, which we kind of fix. So we have a given amount of sunlight. And then I express my results in terms of equivalent mid-latitude conditions. So which means that I can calculate the photolysis exposure in a given day. So instead of having a curve, having a peak during the midday, I actually can calculate the exposure during the whole average day. So these are expressed in terms of average days. So it factors in. You don't see ups and downs, and that's on purpose because we don't want to be perturbated by these changes, diurnal fluctuations. So, but yeah, so.
But maybe when you put it into a regional model or something, you should see something.
Yeah,
like that.
So when you put it in these global models, so because we are scaling to NO2 photolysis, and NO2 photolysis are of course dependent on, they have diurnal dependence, so that's reflected in there.
Are there other questions? And we're using the mic. Who wants to go? Jean-Francois, who's in the back.
Alma, so on this figure, for example, you have a NOx dependence that you're showing for some of the chemistry. Do you have a feel for how much of the SOA between pre-industrial and present day has been affected by anthropogenic emissions, such as NOx emissions?
In this example?
Well, just
in general. So anthropogenic activity actually can affect SOA in different ways. And so NOx emission, for example, is one of the ways. And NOx is going to affect it mainly through reaction with NO3. So that will be the nighttime chemistry. That's where you're going to see the yields with NO3, the production, is really, really big. So that's where you're going to see an impact, positive impact. Then the other way to affect it is you're making basically different type of species. When you are oxidizing your VOC, you're making an intermediate peroxy radical RO2, which can, if you have a lot of NOx, react with NO instead of reacting with HO2. And you're going to make more nitrates and different compounds. And these species are going to be basically, if you have more NOx, they're going to be a little bit more volatile than when you have low NOx. So that's going to push it a little bit down. Another effect of, so that's the effect of NOx. Another effect of anthropogenic activity is that we are generally having more aerosols. And if you have more aerosols due to this thermodynamic partitioning, equilibrium partitioning, you have the tendency to pull more gas species into the aerosol. So this would have a tendency to increase the general amount of aerosol due to anthropogenic activity. So there are many different ways, and some of them kind of cancel each other. So we did studies especially over Colorado here, to see what was the impact of a 50% reduction in NOx, because they're saying they're going to cut one of these power plants, Four Corners power plants. So we wanted to know. And actually, the effect, there was pushing one way because we are making different compounds. And also, the NO3 chemistry was pushing it the other way. OH is also changing, so that also has an impact. So it's not just one linear, simple effect. So there are many ways.
Yeah, thanks, Alma. Well, we all know Gecko is a really incredibly complex model. What would you say the uncertainties are in any given simulation, the magnitude of the uncertainties?
Well, that's a very, very good question. So it's a difficult question because Gecko basically has been validated for different compounds. And some of compounds like these N-alkanes seems to be comparing really well with chamber experiments. So we cannot trust them. And there are more and more chamber experiments to do that. Aromatic compounds, because Gecko inherited part of it from the master mechanism chemistry, they're a little bit more uncertain. So I would say there's some really high uncertainty on that chemistry. There are some new chemical processing, like for isoprene, these epoxides, and that's still not in Gecko. So that's another source of uncertainties. So there are many different uncertainties, and it's really hard to say. But to me, I don't think it's off by, I mean, depending on the individual precursors, but it's probably not, it's within a factor of 2 of the reality. So that's safe to say, I would say. It's not off by a factor of 10 based on all the comparison that we did with ambient data running it in Mexico City or with chamber data, and many other groups are using it. So it has some grounding to, reality. And so yeah, I hope that answers your question.
Thank you. I've got 2 questions, if that's okay.
Sure.
So firstly, you were talking a lot about, from Gecko, like the large N-alkanes and alkenes having quite high solar forming potential, and they're obviously missing from the emissions inventories. So you run through the 3D models later on. Do they not have those emissions?
That's the first question?
Yeah.
So yes, typically the inventories in the US and globally, they stop at C11. So they don't have those emissions. For Mexico City, we have to actually look at and redo these emission inventories. The reason the emission inventories in the US don't have them, because usually these species are very difficult to measure. And there was maybe a couple of studies in LA that estimated them. And they're also, because we are not using these dirty fuels as in some other parts of the world, they might not be as important. They're not going to be the dominant precursor for the US. So it's going to be really dependent on where we are in the world. But I agree with you, we need much, much better emission inventories. And now that we are aware that we also are trying to model organic aerosols, not only ozone, these emission inventories have to be revisited, and we need to include some of these important precursors, which are not in many chemical mechanism or emission inventories. And we are working on that. I mean, that's something very important.
Yeah, that's good. Yeah, no, I was just interested if you thought that was the major part of where we're missing the current production, or if you think it's from other
For Mexico City, yes. Yeah. For the US, I don't think so. And there are actually some global models now that include these, for example, for fires. And they're just so unconstrained that they are making low aerosol again, and they don't have any real constraints to say if it's true or not. So you really have to be careful and really say what you understand and distinguish it from what you're making up.
So the other question was, you had that big map of the changes to soil formation when you have the photolysis.
This one?
That one there, yeah. And you see you have the biggest reduction over the oceans, but there's obviously very low solar loadings there. Is that reduction, but obviously there's very low aerosol over the oceans, and a very small perturbation can make quite a big difference in terms of the forcing, because there's in terms of like indirect forcings. Is that difference actually significant or not?
In the absolute values?
In absolute values,
yeah,
yes.
No, it's not really significant, because we have very small concentrations over there. And also the fact that this process is basically a loss, an exponential loss, if you like, and it's going to be more important as you go 1 or 2 days further down. So that's why you also see this stronger gradient when you are further down the sources. And sources are, of course, over the continents. So, but in terms of absolute mass, no, it's pretty small, because you see that most of the mass is actually over the continent. So.
Nice talk, Alma. What do we know about the optical properties of these particles? Are we ready to put them into radiation schemes and the like?
Fortunately, they're already in radiation schemes. So we actually basically, in all of the models, assume that organic aerosols are purely scattering, just like inorganics, just like sulfates. And that's incorrect, because we now know that we talk about brown carbon, browning of carbon. We know that they also absorb. It's still really an active area of research, so there is we don't have the right measurements. The community is still gathering the measurements to have a confidence to put a different value in a global model. But what's right now in there, purely scattering aerosol, that's wrong already, so we kind of know that. And it's going to depend on the source. For example, if you have a biomass burning plume, or if you have a biogenic plume, this browning of carbon, it's going to happen at different rates. So there's a lot of excitement about that. It's important.
My question is about your second to the last slide, where you're talking about evaluating of the southeast U.S. And I'm wondering, well, this is one of the areas that you look on the map of global change and temperatures, and this is one of the areas that's the lower down effect. It's not getting as hot as the rest of the world. And I'm wondering if your evaluation of the SOAs there can maybe explain that, or what do you think about that?
I mean temperature effects, because aerosols are actually scattering radiation, and so we don't have such a differences in temperature. Yeah, I mean there's much more aerosol down there because we have a lot of forests, a lot of sources, and also there's a lot of, it's pretty humid, so it's probably there's a lot of aqueous phase chemistry going on. And if these aerosols probably are helping reduce the temperature changes in that region, I agree with you. But I don't know, we are modeling, and we are part of NOMADs and SOAS, and we're really using this data to mainly evaluate the models, and we are not doing really predictions for the future. But yeah, it's a good point.
Thank you. And let's thanks Alma again for a very nice seminar.